Recording. There we go. Okay. So now we're venturing to chapter 7. Chapter 7 is a pretty complex chapter. It doesn't get complex until we get to 7.4. 7.1, 7.2, 7.2 are actually pretty easy. And the timing works out great because Spirit Week is in 2 weeks, right? Actually, we're going to be knee deep in Spirit Week 2 weeks from now. And as I promised, I'm not going to do anything too heavy during Spirit Week. Obviously, we're having our test on this before Spirit Week, so Thursday of next week. So in 8 days, we do have another test, a small test again, same weight as the test we had last week and the test before that. 30 minutes, really short. And I'll combine the first two sections because they're both very similar. They're called exponential growth and decay. And the formula right there does look a little wacky, but once we do some problems, you'll be fine. The first thing I want to do is help you understand numerically how an exponential function works. So exponential simply means that you have x in exponents. That's all it means. So exponential means you have x in the exponent right there. We'll discuss domain and range for sure, and how these shapes and transformations all work out. So first off, let's explain what a, b, h, and k represent. A is what we call the initial value. We call a the initial value. B is what I call the base. Also could be called growth or decay factor. That's a G, by the way. Sorry about that. Could also be called growth or decay factor. And I'll explain that in just a couple minutes. H is going to be the horizontal shift. And K will be the vertical shift. That's kind of the typical expectation for transformations. H is horizontal shift, K is vertical shift. Textbooks like use those letters. And so it's A times B raised to the x minus H plus K. More simply, we usually think of like something like this as exponential. Y equals 2 to the x. Here, obviously, A is 1. So even if you don't see it, there is a 1 being multiplied to it. H, of course, is 0 because you're not shifting the graph. K is also 0. And my base, of course, is 2. And that's a very basic exponential function. And if you think about it, you're just doubling, right? That's all you're doing. Like when x is 0, you get 1. When x is 1, you get 2. When x is 2, you get 4, and so forth. So yeah, that's how that graph will look. We'll talk about these graphs in just a little bit. But when b is bigger than 1, so when your base is larger than 1, we call that growth or exponential growth. Let me exponential growth. And by if I'm going too fast, please let me know too. I could always pump the brakes. More than happy to pump the brakes and go to the kitchen and grab a bite to eat. So exponential growth. So then B is called the growth factor. But if B is between 0 and 1, we call that exponential decay. So B is then called the decay factor. Before we answer the questions below, does anyone want to give real life examples of what could of what we can model using exponential growth and what we can model using exponential decay? And we can just chime in or type in the chat. Real life situations. Let's start with growth.
Like things in science. So like Excel, I don't know, something like that.
You said it's about cells or
like something in science.
Sure, yeah, totally something
like
in science. Yeah, you can look at for example, if you're looking at like bacteria growth.
Yeah, that's what I meant.
COVID is totally exponential, guys. Totally. I mean, actually, for a while it seemed exponential, then it slowed down. And that's a different kind of function called a logistic function. I see something in the chat. Let's check it out. Compound interest, totally. Yeah, 100%. If you have an investment account, your money should grow exponentially, right? I mean, the long run, I mean, yes, the stock market, I mean, I did have the Dow Jones here, so it was down, but and that's, you know, that's probably mainly due to Silicon Valley Bank's collapse. But anyway, yeah, but like investments for sure. Home prices in the Bay Area have grown exponentially. Yes, they do go down, but in the long run, if you were to kind of model it, it would seem like an exponential growth. How about decay? What would be something that would you can use to model exponential decay? Think about what's parked in your garage. Do cars go up in price? If after you buy a car, cars go down in price after you own it, right? Once you buy the car, every year the car depreciates, so it's less than it was the previous year because you put miles on it. The car gets, you know, wear and tear. So if you bought a car for say 50 grand, then you drive it for like a couple of years and you put like maybe 20,000 miles on it. You try to sell it, not gonna sell it for 50 grand. Something will sell for less, maybe for 30 or 40, I don't know, depending on market conditions and how what shape the car's in, right? Of course, if you have a classic car, like you have a car from the 60s, you refurbish it and you maybe paid like $1,000 for the car like 50 years ago, and now it's, you know, it's shiny, it looks great, you replace the engine. Yeah, you might be able to sell it for maybe 20, 30 grand because it's a classic car, so I want the classic car. But for the most part, cars are something, or endangered species, like if there's an animal that's you know, being hunted or you know, just not surviving in the wilderness, that could be also used for exponential decay. So so that's just some real life examples. Now let's talk about some technical stuff here. Can B equal 0 if you want to be decay or growth? And the answer is no. That's because y equals 0 to the x power is just 0, right? 0 times anything is 0. So you can't have b equals 0. That's why we don't have the equal sign here. What if it's less than 0? The answer is no again. And that's because weird things happen. If you have a negative base. Let's say I have like -2 raised to the x power. What's going to happen, that's going to oscillate or go back and forth between positive and negative y values. And also, what if x were a fraction, like 1/2? You can't, that's a square root, you can't square root negative numbers. So you have a bunch of, it's just that's just gonna be too weird, right? It kind of does this like weird type of oscillation.
Should we like know the word oscillation? Is that gonna be
No,
like
no, just back and forth. It's fine. Now if h and k are both 0, then a can be called initial value. I already said that. And the reason why is that if h and k are both 0, so you have y equals a times b to the x power. If x were 0, you get y equals a times b to the 0 power. Anything to the 0 power is 1, so you get y equals a. And do remember that for exponents, anything raised to the 0 power is always 1. In case you're curious why that is, let's say I have 2 to the 4 power, right? I know it's 2 times 2 times 2 times 2. What if you have 2 to the 3 power? I know it's 2 times 2 times 2, right? You don't have to write this down, just explain why 2 to the 0 power is going to be 1. 2 squared, that's 2 times 2, right? 2 to the 1 power is 2. And all along, without realizing it, there is an invisible 1 being multiplied all these numbers, right? For all these powers, right? 1 times anything is itself. So there is a 1 here the entire time. So when you get down to 2 to the 0, you don't have any 2's anymore, but it's still a 1 being multiplied to the left of it. And that's why it's 1. So anything raised to the 0 power is always 1 for that reason, in case you're curious. Okay, let's actually get to the nitty gritty. Let's do some graphs. And just to pace ourselves, we have example 1, example 2, example 3, and an example 4. And I'm not doing 7-3 today. Okay. So we're going to start very basic with examples 1 and 2. So y equals 2 to the x. So whenever you just start doing a graph, and this is growth, by the way, this will be growth. It's always good to do a table and plug in some easy numbers for x, like say 0, 1, and 2. But let's do some negative numbers also, just to see what happens. So you do 2 to the 0 power, we now know that's 1. 2 to the 1 power, we know that's 2. 2 squared, I know it's 4. Now negative exponents. Negative exponents you flip, right? We talked about that in the previous unit. That's 1/2. So you flip the base and it becomes 1/2. Or 2 to the negative 2 power, you flip 1/2, then squared, that's 1/4. So, you have 0, 1, 1, 2. Ooh, that's a nice color. I don't usually use that color that often. 2, 4. In negative 1/2, be really careful because you have some fractions. And so the graph is going to look kind of like this. So here's a question now. Let me put it as a text box. Will the graph of y equals 2 to the x power ever cross the x-axis? Also, will y, sheesh, let me fix this, ever be negative for this equation? So what do you guys think? You could just type in the chat yes or no. Yep, it's no. It's no for both. Fully no for both. And here's the reason why. If you plug in more negative values, like say you do -10, right? So you go more to the left. 2 to -10 power, that's just 1/2 raised to the 10 power, right? Because the negative exponent causes the base to become a reciprocal. Well, if I multiply 1/2, 1/2 is a positive number. There are no negative numbers involved, right? 1/2 is a positive number. I'm multiplying 1/2 10 times. Of course, it becomes really tiny. In fact, if you're curious, I think it's 1/1024, if I'm not mistaken. I could be wrong, but it's a super small number. It's like 0.001. So it gets awfully close to the x-axis, but it never becomes 0 because of the fact that my base is 2. My base is positive. I can never make that negative because I don't have any negative numbers to multiply, right? That's just how a power works, right? You have a base and you multiply by whatever exponent you see. So yeah, this will never be 0. And it will never cross the x-axis, because if it does cross the x-axis, it would be 0. Meaning it will never be negative either. How can I make this negative? I can make it negative if I put a negative out in front. Then I flip the graph. We'll talk about that later. But y equals 2 to the x can never, ever be negative, never be 0. So thank you for those who chimed in. Some more people chimed in and said no, that's good. But then on the right side, it does go up forever, right? Because what if I plug in like, so that was 1/1024 for -10. What if I plug in +10? Then I'm multiplying 2 10 times. That's a big number. I'm multiplying 2 10 times. So it goes up like crazy, right? When you hear things increasing exponentially, that means that it's going up forever, right? It's going up really fast too. It's becoming more steep. So sometimes they'll say like if like the rabbit farm, those animals, they reproduce exponentially, or rodents, which are ghastly. I hate rodents, but same thing. They reproduce exponentially, right? So anyway, when you hear things increasing exponentially, it means it's growing pretty quickly, and usually you're multiplying by a base over and over and over again. Now, another thing I need to add here too, which is a new concept. And I really want to be careful how I teach this, because some people can really have misconceptions about this concept. See this dashed green line? We call this an asymptote. Okay, and let me be careful how I define this. That's called an asymptote. And it represents the end behavior. Now, you guys did talk about end behavior when I was on paternity leave, when you did polynomial functions. End behavior means how the ends of the graph behave, right? how the end of the graph behaves. Well, if you think about it, the left end looks like a horizontal line, right? Totally looks like a horizontal line. The right end obviously is curved and it's shooting up, but the left end totally looks like a horizontal line. More specifically, it looks like y equals 0 or the x-axis. In fact, it's almost like grazing the x-axis, the left end of the graph. So that's what an asymptote, more specifically, this is what we call a horizontal asymptote. Vertical asymptotes we'll talk about in the second half of chapter 7. We won't do that until after spring break. But this is what we call a horizontal asymptote. So it's really describing the end of the graph. That's what it's for. It's an equation that describes how the end of the graph behaves. We'll talk about how to actually identify asymptotes once we finish off these notes. Now, some people will think that this is a barrier you can't cross, which it initially seems kind of true, but that's actually pretty far from the truth. So kind of like a barrier, but not really. Because there are going to be some cases, especially when we get to chapter 8, where we're going to have horizontal asymptotes, and the graph can cross the horizontal asymptotes. Horizontal asymptotes can be crossed depending on what kind of function you have. For now, they won't cross them because that's just how exponential functions are. Kind of like a barrier, but not really. It's really how the ends of the graph behaves. That's how you want to think of it. Sadly, there are some teachers who teach as a barrier in the context of this problem and don't really kind of tell the students like, well, there are going to be times where you can cross a horizontal asymptote, and then they are surprised when they take a class like this or pre-calculus, and when you see other types of functions, not exponential, but other types we'll learn, and they see that, oh, you can cross a horizontal asymptote. I didn't know that. So I want to make sure you guys are learning this correctly. So I'm kind of putting on my calculus and pre-calculus hat on to make sure you guys are not having this misconception of this concept, because sometimes it is taught incorrectly. Go ahead.
What does the purple say again?
Oh, kind of like
Right.
a barrier, but not really.
Okay.
It kind of looks like a barrier, but not really. Like it looks like it's a part we can't cross, which is true for now. But we are going to see in chapter 8, which is going to be something we'll do like late April and May, that we'll have these graphs that can cross horizontal asymptotes. So, but we do have to show this. So I know there's a lot of stuff going on here. Let me actually delete that. Domain range. Let's get that out of the way. Let's do that in red, and then we'll move on to number 2. Domain range goes from negative infinity to infinity. Sorry, domain. Because the domain, there's no reason why there'd be a restriction for x. You can plug whatever you want for x, right? Range, however, you're going to say from 0 to infinity. And not included, right? So you want a parentheses, not a bracket. Because this can never equal 0. How can you multiply 2 over and over again and make it 0? You just can't, right? In order to get 0 as a product, you need 0 involved in the situation, right? You need to be multiplied by 0, but we're always multiplying by 2. So y can never be 0. So you got to understand numerically that y can never equal 0 here. Can never, ever, ever, ever equal 0 because you're multiplying 2 over and over again. Haley, go ahead.
Is that a bracket around the infinity
No,
sign?
it's
The range?
parentheses, all parentheses.
Oh, shoot. Okay. That's what I thought, but I
Yeah,
didn't know.
yeah, sorry about that. Yeah, because infinity is this abstract idea that we just don't know what the biggest number is. It just keeps going up forever, Let's make it a little more rounded. Sorry about that.
Okay, and then the 0 is also like
It's also parentheses because y equals 2 to the x. Y can never be 0 numerically. If you think numerically, yeah, like how can I get that to be 0? You just multiply 2 over and over again.
oh, okay. Thank you.
Yeah. So that's why the graph grazes the x-axis. It gets really close to it. Like, if you plug like negative 1,000 for x, then you got 2 raised to negative 1,000. It's like 0.000000001, by the way. Very, very tiny. kind of like your chances of getting a perfect March Madness bracket. By the way, does anyone know the probability of getting a perfect March Madness bracket? If anyone knows without looking it up, well, I don't know if you're looking it up. If you're looking at offer extra credit. If we're in the classroom, I would ask that. Wait, does anyone know the probability of getting a perfect March Madness bracket? It's really low.
1 in 9223372. It like goes on for a long time.
Yeah, I think it's a quadrillion, if I'm not mistaken.
Yeah, it's like here, it's that.
Yeah, there you go. Yes. It's a very low chance because there's 63 games, not including the playing games, by the way, 'cause it doesn't count. But the field is 64. There's 63 games, and so yeah, so that's an exponential decay, or kind of exponential in a way, because yeah, it's a really low probability of that happening. If you can do that, you should not be in school. You should go to Vegas, make money. So anyway, let's keep moving here. So now this is 1/2 2x. So now this is just kind of the same thing, just goes in opposite direction. So I'm gonna tell you right now, the domain is still going to be negative infinity to infinity. I'll tell you that right now. The range is still going to be from 0 to infinity. And we're still going to plug in the same numbers as before. But 1/2 to the 0 power is still 1. That's going to be 1/2 and 1/4. And then this gets reversed. If you do 1/2 raised to -1, you flip the base, which becomes 2. If you do 1/2 to -2 power, you flip the base and square, that becomes 4. So everything gets reversed compared to 2 to the x. And this is going to be decay, not growth, because my base is between 0 and 1, not bigger than 1. So we call this decay. So -1, 2, -2, 4, 0, 1, blah, blah, blah. And now it looks like this. Yeah, you still have an asymptote, horizontal asymptote. Y equals 0. And so as x gets larger, as x approaches infinity, y is approaching 0. That's another way of thinking about it too, as kind of a limiting case. As x gets really large, like if I'm playing like 10, y only gets smaller, but it doesn't get exactly 0, right? Because how can you make that 0 if you don't have a 0 involved in your multiplication process, right? You're always multiplying 1/2, not 0. And of course, when x gets more negative, so you plug in -10, then you're flipping the base and doing 2 to the 10 power, which is really large. So you can see how there's a decay, there's a decline. For those who are taking chemistry, I'm not sure if you guys learned about half-life, or maybe in bio you guys did. Half-life just means the time it takes for some material to decompose to half of its previous amount. That's also a decay function. So someone said science, yeah, you see exponential functions all the time in science. So that's that one. Pretty simple. And I think these correlate to examples in the textbook, I think. This might be a previous, actually, I don't think I think the additions stay the same. If you don't have textbook, don't worry about it. But if you do, these all come from the textbook. Okay, now let's do some stuff with transformations. We'll do a transformation with growth and transformation with decay. Then we're done with the notes, and then we'll do some classwork. And also we'll stay on the Zoom call, and I won't do breakout rooms because I think the breakout rooms kind of stink. I kind of want people to chime in if they have questions so other people can hear. And we're a small enough group, we know each other well. Yeah, breakout rooms I thought were pretty so one thing I think that made the Zoom classroom pretty terrible 3 years ago. And of course, this is not the most ideal way to teach, but we'll make it work because we don't have to fall behind, right? That's important. So thank you for being here. But let's talk about this one. Okay, so you have 4 times 2 to the x minus 1 minus 3, right? So here's the deal. Let's identify A, H, and K. And of course, our base 2. Our base is 2, that's obvious. Our A is 1. Sorry, A is 4, yikes. Our A is 4. our h is 1, and our k is -3. Right? Because the general formula is this, which I'll give to you guys, by the way. You don't have to memorize, but when you do enough of this, you kind of just know what's going on. But I'll give it to you in case you're worried about that. But I won't tell you what h and k represent. Obviously, you got to know that. So your initial value is 4, h is 1, k is -3, and b is 2. Okay. So if we look at the parent function first, and then we'll make some adjustments. The parent function is when a is 1. Whenever you have a parent function, a is 1, h is 0, and k is 0. And you keep b the same. That's the parent function for any of these exponential. Like if I had a 3 as my base, my parent function would be y equals 3 to the x. If I had a 5 as my base, or 4, it would be 4 to the x or 5 to the x, right? So when I make a table for the parent function, we know 0, 1, 2, -1, -2. I'm going to do 5 points just to be on the safe side. So 0, 1, 4, half, and 1/4. So it's pretty clear that h is 1, so I've got to add 1. So this means add 1 to x. So that's what I'm going to do. I'm going to add 1 to x. 1, 2, 3, 0, -1. Boom, there we go. A is 4, so I'm going to multiply y by 4, then subtract the result by 3. So if I multiply this by 4, let me minimize this window here. Multiply by 4 and then subtract 3. Multiply by 4, 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 subtract 3. I know it sounds like a broken record, but that's precise what we're doing because of PEMDAS. So the first will be -3. Then it'll be 1. Then it'll be 13. Then it'll be -1. And then it'll be -2. So when you do it this way, you're very calculating about it, right? You're very methodical. And then you have the graph correctly. Plus, if you plug 1 into this, right, you're gonna get wait one sec.
Isn't it when x is 0 that equals 1?
Hold on.
Is
Yeah,
that
yeah.
exponent?
Did I make a mistake somewhere?
In your parent function?
When x is 0, oh my goodness. Wow, I can't believe I did that. Yeah, thank you. Thank you for correcting me on this. Okay. Well, it's an easy fix. Okay. It's a real easy fix. Yikes. Wow. I can't believe it. Thank you. Thank you. Thank you. Thank you. Thank you. So yes, so I knew, okay, so how did I catch myself, right? Well, first of all, was that AJ who corrected me?
Yeah, it was.
Thank you, AJ. I appreciate it. Yeah, so you see, now I know your guys' voices because I've seen it. But 3 years ago, like people speak like, who are you? And then I see him like a year later, like, I didn't know you were in my class. No, but thank you, AJ. I appreciate it. I digress. So yes. So what to check my work, it's good to have another person chime in. So please speak up when I make mistakes. But also when I plug 1 back in, right, just to make sure I did the transformations correctly, I realized, wait, something's off here, right? Because 2 to the 0 power is 1. 4 times 1 minus 3 should be 1. Why am I getting -3? That's because my parent function was wrong. So if I do it again, that should be 1, and that should be 5. Okay, much better. If I plug 1 in, I get 2 to the 0 power, which is 1. 4 times 1 minus 3, yes, 1, 1. Oof. All right, there we go. 2, 5, I know that's correct. 3, 13, way up here, which I didn't leave myself enough room. 0, -1. So this does go below the x-axis, and that's okay because of the transformations. -1, -2 is right here. And here's the deal. I know this part right here can never equal 0. Because you can't multiply 2 over and over again and make it 0. And you multiply by 4 afterwards. So I know, and if I make x really negative, I plug like -10 for x, I'm doing 4 times 2 to the -11 power, which is a super small number. because 4 over 2 to the 11th power, which is really tiny. So I know that this gets really close to 0, the 4 times 2 to the x minus 1 part, and then you guys subtract 3 after that. So what's going to happen is that the curve is going to do this. So there is a horizontal asymptote, but it got shifted down by 3 units, as it should, because k was -3. So the parent function, y equals 2 to the x, look like this, which I do in light green. And because you're shifting 3 down, the horizontal asymptote also comes 3 down. So it's at y equals -3. That's your horizontal asymptote. That means that the range will also be affected as well. The range will be from -3 to infinity, non-inclusive for -3. The domain's still all real because you can plug in whatever you want for the exponential functions. The domain's always going to be all real for exponential. Just in this chapter, our domain's always all real. Just so you know, for everything we do in this chapter, the range will change depending on. Actually, yikes! I meant to say for everything we're doing in chapter 7a. 7b, the domain will change. I apologize. Take that out of your head. After spring break, when we do the second half of chapter 7, the domain won't be all real. And you'll see why in a couple weeks or 3 weeks. But for exponential functions, that's what I meant to say. Domain's all real for chapter 7a, exponential functions. And range will change. So questions on this one before I move on to our last example? Nope. Okay. And again, I'm going to try to stay true to my word and end this before 9:50. I'm hoping we can end by about 9:40, so that way you can do a little bit of practice, and of course have a break for your 10 o'clock class. And maybe your 10 o'clock class might be asynchronous. I don't know, but I want to do this live because just math is done better live, I think. All right, last one here. So my parent function is y equals half to the x. So my a is 3. My h is going to be -1, by the way, because it's +1. K is -2. And my b is 1/2. And the parent function, again, if I do it over here, I'm going to do this correctly. I'm not going to make the same mistake I did last time. 0, 1, 1, 1/2, 2, 1/4. And then -1, -2, I get 2 and 4. Nice, nice, nice. Yeah. So now let's make the changes. So to make the changes, -1, you're going to subtract x by 1. So for example, if I want 0 as my exponent, I need -1 for x. And I'm just going to take 1 away from each of these. That's easy. And then here, you're going to have to multiply y by 3. Then, remember PEMDAS, right? That's why I spent all this time in PEMDAS. We can't mess this up anymore. Then, subtract by 2. So multiply 3. Subtract 2. 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 So I'll get 1. -1/2. Careful there. Ugh. -5/4, I think. 4 and 10. So it's going to be way up here for -3, 10, -2, 4, -1, 1, 0, -1/2, and 1, -5/4. So the graph kind of shifts down like this. So our vertical asymptote, sorry, our horizontal asymptote is y equals -2, because of the -2 there. So everything shifted down. From the parent function was like this for half to the x. So you shift down 2 units. Domains, of course, all real, as I said earlier. Always be all real for exponential functions. For the 7a unit, not all chapter 7. And then the range will be from -2 to infinity. And again, this part right here, which I'm highlighting in yellow, can never equal 0, right? Because how can you multiply half over and over again and make it 0? You can't. You can get close to 0 when x gets really large. Like if x is 10, you're doing 3 times 1/2 raised to the 11th power, which is a really small number. Then you subtract 2 afterwards. So yeah, so there we go. There's our graphs on exponential growth and decay. Let me go ahead and end this video.